Hello! So, as promised, I want to review the elementary functions just to make sure that we're all on the same page. Now, I'm having some technical issues with getting my beautiful visage to show up on this video screen today, so in the meantime, you can look at my cat. Oh. The functions I'd like to start off with, let's get the difficult ones out of the way. I'm going to look at the exponential and logarithm functions together. So let me graph here. Y is going to be e to the power, and I'll write ax. I'll put in a little slider for a. So this is the basic exponential function, and it comes in a wide assortment of flavors depending on what constant we put here. So for a equals 1, this is exactly the same function as y equals e to the x. There I have it. And if I change that parameter, I can make the curve steeper, or I can make it shallower, or I can make that parameter negative, and now I have exponential decay rather than exponential growth. But all of these would be examples of exponential functions. The cousin to this function is the logarithm function. So if I'm looking at, again, let's have just a equals 1. So there's my basic y equals e to the x. I'm going to look at the natural logarithm function, which I can graph as y equals ln of x. So immediately we can see there is this nice mirror symmetry between the two functions. And the reason for that is that the natural log and the exponential function undo each other. So you might have seen things like e to the power of ln of x. Why, that's just our good old y equals x. But only for positive values of x. The natural logarithm is undefined for negative numbers. I can also go the other direction. I can say, what is the natural log of e to the power x? And now, again, I have my nice y equals x. So these two functions are canceling each other out. And now this formula is valid for all values of x because any value of x can be run through the exponential function. Now, if I tighten this curve, I lose that property, right? These are no longer mirrored, so they're no longer inverse functions. So just like there are lots of different bases for the logarithm, I'm getting ahead of myself. Just as there's lots of different bases for the exponential, there are lots of different bases for the logarithm. So one way we can notate that would be y equals log, and as a subscript, I'll put an a, this is my same parameter a there, of x. And I'll turn off this curve for right now. So now as I change my curve, my parameter, both of these change. So whatever your base for your exponential is, this is the logarithm which undoes it. I can rewrite this formula here. Let's say this is e to the power, e to the power a, then to the power x. That is exactly the same formula. Things get a little weird for fractional values. Don't worry about that too much. But there is a nice family of curves. So both of these operations, taking an exponent or taking a logarithm, have lots of interesting algebraic rules to them. I'll quote some of them here. So e to the power x plus y in the exponent is the same as e to the power x plus e to the power y. If I have e to the power x times y in the exponent, that's equal to e to the power x in parentheses, and then all of that to the power y. Oh, and never mind the picture. Desmos is trying to interpret that as a graph. I'm sure that would be a lovely thing to think about, but that is not what I'm prepared to lecture on at the moment. And corresponding to these formulas, the logarithm also has special algebraic properties. So whatever your logarithm of choice, I'm just going to use log for the base 10 log. Log of x times y is equal to log of x plus log of y. And again, I'm not going to actually graph that. And if I have powers inside of that logarithm, log of x to the power y, this will be equal to y times log of x. Now, these formulas work for any kind of logarithm you like, whether that's a common log or a natural log or even some other base, just the same as these formulas will work for any exponential function, whether that's e to the x, 2 to the x, pi to the x, a million to the x, and so on. So that's all that I have to say about these functions for right now. And please feel free to rewind this video if I have been talking too fast and you'd like to hear it again. See you in a bit.